All right, we're going to talk about the sinusoidal steady state solution. What that really means is that we're heading towards a discussion that's going to involve sources that vary sinusoidally. A source could have a voltage function that looks like this. Let's do cosine. We could do cosine or sine there. It doesn't really matter. Understand that a sine and a cosine are technically the same, but they're shifted by about 90 degrees. Well, exactly. They're shifted by 90 degrees so that it really depends upon where you want to start these things. But we can describe it this way. The voltage function is going to have an amplitude, that's this V sub m, an angular frequency, that's this omega, that's not a W, that's a small Greek letter omega. And then this right here, that's the phase angle. Now, each one of these three parameters are going to give us a handle in describing the voltage function. Now, if you were to think about what this is going to look like, it might look something, like this. Very poorly drawn cosine curve, but you get the idea. The amplitude here, the maximum value that each one of those is going to have is this value right here, V sub m. And then down here is negative V sub m. So this is the amplitude of the curve. It's this height right here or this depth right there. Now this omega is the angular frequency and it has units of radians per second. Now radians per second, since radians are unitless, we usually call that 1/seconds, and that known by another name is called a hertz. So a hertz is a something per second. So this omega determines how quickly the oscillation occurs. So imagine this sine curve squeezed together or spread apart. That's the goal, or that's the thing that omega controls. How many cycles per second or how many radians per second happen. So something with a large omega, you can imagine this being back and forth very quickly, with a very small omega even more stretched out than what we've got drawn here. Okay, the last parameter here is phi, and that's called the phase angle. And what that does is it controls where these maxima and minimum lie. So imagine that we take the curve itself and we shift it left and right. That's what phi does. So phi has the ability to shift the whole curve itself left and right. And that's what I mean when I say the sine and the cosine are essentially the same function, because if you take, say, this point right here in the cycle and you move that point to right there, then we've essentially created a sine function out of this and it's no longer cosine. Okay, so we could make that like 90 degrees, plus or minus 90 degrees, and we could cause it to do that shift right there. Okay, so these three parameters then are the parameters that we need to fully describe any source. Now I will say one other thing about this angular frequency. This is the angular frequency, but there is something that's just called the frequency. We'll symbolize that with F. Now, if we're talking about a power supply coming out of a wall or maybe a generator, then that F, at least in the United States, is usually 60 hertz. So when you talk about 110 volts, 60 hertz as the power supply that's coming out of a wall socket, the 60 hertz is referring to this frequency here, not that frequency there. Now, the difference is subtle because this is radians per second, omega is radians per second. This is just cycles per second, but they both have the same unit. They both have hertz. So you're going to have to rely upon the context of the discussion to know if you're talking about F frequency or omega angular frequency. But when we plug it into the cosine or the sinusoidal function here, it's got to be in units of radians per second. Okay, because when we multiply by t, it's going to be radians here, radians here. So what's inside the parenthesis here has to be an angle, and it's almost always going to be expressed as radians. Okay, we'll probably talk more about that a little later. All right, one other thing relating to this frequency, and that is period. The period is how long it takes it to go through one complete cycle. So from this point here to that point there, the amount of time in between here and there, that's the period. So the period is usually symbolized as is just capital T, but the capital T is related to the frequency as a reciprocal relationship. So the period is 1 over the frequency, like that. So if this is inverse seconds, 1 over seconds, that's what a hertz is, then the period is the reciprocal of that, so period is going to have units of seconds. So you can think of this as the number of seconds per cycle. You can think of the frequency as the number of cycles per second. They are reciprocals of one another, like that. Okay, now given that we have a voltage function that looks like that, let's think about what the current would look like for various components that we've talked about so far. We'll go into this more later, but I want you to get a handle on it right up front here. First of all, the current, I, is going to be V over R for a resistor. Now that V is the voltage across the resistor, the I is the current through the resistor. And you know that if you took this voltage function, we are assuming that this is the form of the voltage function across the resistor, just the form of the voltage function across the resistor. When you plug that in here, you're going to end up with some sort of amplitude. It's not going to be exactly that. In fact, it's going to be V sub m divided by R multiplied by the cosine of omega t plus phi. Now here's what I want you to get. I want you to notice that the voltage and the current functions look almost identical here for a resistor. The thing that's different is the amplitude out front, but they have the same frequency and exactly the same phase angle. Now that may not be the case. In fact, it will not be the case for the other components that we're going to talk about. For example, the capacitor, I is equal to C dV dt. That's the relationship between voltage and current for a capacitor. So that's the current through the capacitor. This is the voltage across the capacitor. Okay, now imagine that we take this voltage function, we plug it in here. What we're going to end up with after we do that is we're going to have some amplitude out front. You could go through this process if you want to. I'm just describing it in general. We'll talk about it more later. But you're going to end up with something that is actually going to be some sort of sinusoidal function. And there's going to be an angle here. In fact, that angle is going to be exactly the same. But if you take that sine and you change the phase angle, you could rewrite this in terms of an amplitude times a cosine, and the cosine is going to be omega t plus a different phase angle. Let's call this one phi sub c, just to indicate that this phase angle is different than this phase angle. But the omega t is exactly the same. In fact, this would be omega t plus phi, and all that we've done here is we've changed the sine into a cosine by shifting the phase angle. Now, this is the point that I want you to get. The voltage and the current for each one of these cases here has exactly the same frequency. And if we were to do this same sort of thing for an inductor, what's that going to be? I sub L is going to be 1 over L times the integral V dt plus I at 0. Take your V function here, plug it in, and you're going to end up with some sort of amplitude. You would have a sine of the angle, but then you could do the shift and you could rewrite that as an amplitude multiplied by a cosine omega t plus phi, and let's call this phi sub L, because this phase angle is not the same as that phase angle, and it's not the same as that phase angle. So once again, though, notice the frequency, the angular frequency is exactly the same in all of these cases. So here's what you need to take away from this. If I have something that is modulating the voltage, let's say there's a generator or a wall power supply that is modulating or that is controlling or hooked up to my circuit, and it has a certain given frequency, then that frequency is the frequency that's going to be on all of the components that are in the circuit, okay? So the phase angles are going to be different. The amplitudes are going to be different for all of these, but the thing that's going to be the same is the frequency. So when I say the frequency of the source controls the circuit, that's what I mean. The frequency of the source is going to be the frequency that shows up in everything else that we do, all right? So I just want to introduce that. And you can see that for each of these, the currents and the voltages, they're all going to be sinusoidal. And you can express that as sines or cosines, but we just want to be consistent in how we express it here. All right, we're doing some preliminary stuff before we dive in, so here's another thing that you need to know. Let's say that we have something like that sinusoidal function, looks something like that. This is going to be the time axis, this is going to be the whatever, the voltage axis or something like that. And now this is a voltage function. So this is V sub m cosine omega t plus phi, okay? And those values are the three values that control this shape. All right, now here's a question. What's the average voltage? I see the voltage is going to change over time, so instantaneously, if I knew what instant in time I was talking about, like what moment in time, I could just look along here and tell you what the instantaneous voltage is. But that voltage varies over time. In fact, it varies very quickly usually. So something better than instantaneous, instantaneous only good for that instant in time, might be to talk about what's the average. But there's an obvious problem here, and I think you see it. The average of any sort of sinusoidal function is going to be zero. If you were to sum up, let's say you were to sum up over one cycle. So this, that's not one cycle there. Let's start there and go to here. So the time in between here, that represents one period of oscillation. And we want to figure out what the average is over one period. Well, if I'd have drawn this a little more carefully, it would be more obvious. But if you took all of that area right there and all of that area right there and added them together, you should end up with zero, because you've got positive above, negative below. It's going to sum up to be zero. Okay, so if we're going to talk about average voltage and we've got these sinusoidal things going on here, then we need a different way to talk about this. And here, there is a method to do that, and here's the way the method works. So let's say we want to know what is the average voltage. Well, it's not called average. It's called the RMS value. And RMS stands for root mean square. And those words are an indicator of exactly what you do in order to figure out what this average is going to be. So let's say we want V, and the way you express that is you put a subscript RMS on it. So V RMS is equal to, well, you take your voltage function here, V, and then you square it. Now, when you square it, what you're doing is you're taking the negative portion and you're making it positive. So now you've got another, just essentially flip it about this horizontal axis here by squaring it. All right. Then what you want to do is you want to take the mean, and it's going to be the mean or the average over one cycle now that you've squared it. And the way that you express that is you take the sum, and we're going to sum it over one cycle. So we're going to start at some time t naught, And then we're going to go to some later time, t naught plus 1 complete period. And we're going to sum it up over dt. And after we sum it up, we're going to divide by that period. So there, we've taken the mean of that voltage over one cycle, and after we've squared it. Now, to make up for the fact that we've squared it, what we need to do is we need to do the opposite of the square, and that is take the root. And that's why it's called the root mean square, okay? So that represents not an average, but something that's like an average, all right? It's like an average for a sinusoidally varying function that would otherwise have an average of 0. This is the normal way then to talk about those averages. All right. If you were to take this voltage function here and you were to plug it in as V here, do the square, integrate over 1 complete period. What's 1 complete period? You know, from 0 to 360 degrees, or from 0 to 2 pi. And then figure out what that period is. And you were to go through the mathematics of doing this. Here's what you would find. This is equal to V sub m divided by the square root of 2. Now, that is just a product of the mathematics that happens when you take a sinusoid that looks like that and plug it in. You'll get the maximum divided by square root of 2. Now, we were talking about the voltage RMS, but this would also work for the current. The current RMS is going to be whatever the maximum current is divided by square root of 2. So regardless of what you're talking about, if you need the RMS value of some sort of sinusoidal function, then you just take its maximum divided by square root of 2, and that's what this whole root mean square turns out to be. All right? So given that, then you can just jump to, if I say, what's the RMS value of this voltage? Well, you just take the maximum divided by square root of 2, and you're done. So you know what the answer is going to be. Okay, so that's another preliminary thing out of the way. Let me show you something else. Whenever we start talking about sinusoidal responses here, in general, you have solutions that have a transient component and a steady state component. In other words, whatever you're looking at, be it voltage or current. Oh, by the way, back up here. This root mean square idea works great for voltages and current, just to take the maximum and divide by square root of 2. That's not going to work for power. That's not going to work for energy either. And that's because those are not nice linear functions like voltage and current. Those involve square terms, so you have to keep that in mind. Now, back down here. When we do when we solve a circuit, regardless of whether we're looking for voltage or current, what we're going to discover is that there's going to be a transient portion. In other words, when you flip the switch or start at t equals 0, there is something that happens early on that eventually dissipates. And by eventually dissipating, you know, that means there's probably going to be a decaying exponential involved here. So the transient part eventually goes away, and then all that's left is the steady state part. Okay, so that's really, when we're talking about sinusoidally varying sources here, that's really two different parts. And you approach each of these parts differently. What we're going to concentrate on is the steady state portion of the response. And let me show you kind of what we're talking about here. Let's say that we have a relatively simple circuit that's got a resistor and an inductor in it. We're not even going to put a capacitor in here. This switch is closed at t equals 0. There's some R value and there's some L value here. And then this is the voltage source, but the voltage source is going to be sinusoidal. So the V sub S is going to be some V sub M times the cosine of omega t plus phi. So that's the form of the voltage that is the source for this. Okay, well, if you were to go through and solve for the current here, you're going to find that the current is also going to be a sinusoidal type of function. But the current is going to have a transient part and a steady state part. If you were to follow through with this and figure out what I as a function of time looks like, well, here's what you would find. I as a function of time is minus v sub m over the square root of r squared plus omega squared L squared times the cosine of phi minus the inverse tangent of omega L over r multiplied by e to the negative rt over L plus v sub m over the square root of r squared plus omega squared L squared times the cosine of omega t plus phi minus the inverse tangent of omega L over r. Okay, that's what the whole solution looks like for the current here. Now, look at this, because you can see this first part here is all multiplied by this exponential, which is going to be a decaying exponential. So as time goes by, t gets larger and larger, this is going to decay. And this first term here that's in the square brackets is eventually going to go to 0. It's eventually going to decay. Why? Because remember, exponentials always win. So the exponential is going to decay at a greater rate than anything else that happens here. Okay? And what does that leave? That leaves this portion down here, which is the steady state portion. And you notice the steady state portion has an amplitude, a frequency, and the frequency, by the way, is exactly the same frequency as this. And then what this is, all of that right there, that can be written together as a phase angle. So again, what we end up with is a current that is the steady state portion of this that looks very much like what I described previously. An amplitude, the same frequency as the source, but the phase angle is going to be different than the phase angle of the source over here because of these various components that we've got there. Okay, so there's some preliminary stuff that you need to keep in mind. First of all, the steady state solution is going to be sinusoidal. That's this part right here. There is a transient solution, but for the most part, we're going to ignore the transient solution and concentrate on the steady state. The reason for that is because we need a little bit more information to get to the transient solution. And if you take the second semester of this class, you will get a transient solution. Okay. The other thing, frequency of the response is the same as the frequency of the source. The maximum amplitude here is related to these various components as well as the maximum amplitude of the source, but they're not exactly the same. They're probably never going to be the same. And this phase angle is also not equal to the phase angle of the source in any way. So in order to solve for this kind of thing right here, what we really need to solve for is this amplitude and this phase angle. So keep that in mind. Let's say that this is our source. We're after the current. We kind of know the general form of the solution. The general form of the solution is an amplitude multiplied by the cosine of omega t. The omegas are going to be the same, plus a phase angle. So if we can figure out this amplitude and this phase angle, then we can solve this circuit. Okay? That is really what we're after for the steady state solution. Let's figure out how to get the amplitude and the phase angle, and then once we've done that, well, we've got the answer then.